it is now recording. What I'm just going to do is start up the presentation. Always does that, so I need to flip my screen. Right, so again, welcome to MP3672. This is engineering simulation. We will be considering two different elements of the simulation processes. One will be looking at the static stroke almost dynamic simulation, where we'll be looking at FEA, so the finite element method, looking at meshing in particular, and looking at the way meshing behaves, how meshing is formatted, and looking at the stiffness matrices. Best way to consider a mesh is kind of like a spider's web. My lecturer who got me started in this was Tony Broad, and he always told us that the FEA mesh is very similar to a spider's web, and he's absolutely right. The way that two individual connecting points are connected, you have an elastication between them two, and that elastication can be attributed to what we know as a K value. And as a K value, when you're thinking about a dynamic system, that tends to be referring to a spring stiffness. If you think of that spring stiffness, but then relate that to the elastication of a material behaviour, you end up with a Young's modulus, but the Young's modulus for that elastication. And then what you end up with is something that's elastic, that will move, that has a material representation. That's a very, 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 very big summary to a massive topic. But we are going to go down that road. We're going to jump down the rabbit hole with that. I won't spend masses and masses of time looking at the stiffness matrices. We will be looking at it because you guys really need to know that the most important thing on an FEA simulation is the meshing representation. Because where these connecting bars hit each other, the nodes, where these nodes sit, are a representation of your model. They are only the cloud-based representation of the model. So the mesh is what does all the work. The model just gives a rough guidance. And the aim of the game in meshing is to try and match it against what you're doing and try and find the most ideal scenario for it. We will really go as deep as we can with that, but at the same time I want to prioritize getting the solution, because a lot of people can kind of go, yeah, it's okay, let's just simulate it. Simulation is good, don't get me wrong, simulation is very good. Simulation will never ever do away with prototype. And rather than me just telling you that, what we intend to do is really go down deep so you're aware of why it won't, so you know why it won't. Until somebody comes up with, somebody nicknamed it the super mesh, which, yeah, sounds like something from The Boys. But the idea of the processes, as I said, we will be going quite deep into that because I want you to be aware of that. We will be looking at really important elements to it, but before I rabbit on too much about FEA, for FEA we will be using two separate softwares. I'll be using SolidWorks simulation software, and I will also be using COMSOL. COMSOL, for anybody who doesn't know, is the sister company to Matlab. COMSOL was originally called FEMAP and became big, became its own right, and what we'll be doing is we'll be using a combination of COMSOL and Matlab together to run independent studies. So let's say, for example, we're going to do a study on a dog bone and we're looking at material verification. If we want to do that, what we can essentially do is take that design, set up the simulation, put it into Matlab, and then get Matlab to iterate 1,000 different configurations. Then what Matlab will do is it will bring all them nodes together. You can do your statistical analysis and you can take your averages. It really sets you up big time for being able to have quantifiable data, because a lot of the time when you're producing simulations you get to the end and kind of go, it's good, but is it right? Is it the right way forwards? So you need a good solid argument for that. We will also be looking at Matlab in a form that I know I can feel that from especially the energy guys, well, from the energy students sat in the audience to the mechanical guys sat in the audience to the Matlab, to the CAE guys sat in the audience. You three, I know you did engineering applications in year one, and when Matt had you going through stuff, you'd have gone, oh, this is so boring. But I promise you, what we're going to do is we're going to use Matlab in a way that you've never seen it used before. Some of you might have done, because I rabbit on a lot about using it this way. But we're going to use it in a new way. We're going to use it where some of that stuff that you learned with Matt, in fact, a lot of that stuff will be a benefit to know. For those of you who didn't sit it, don't worry. It doesn't mean that you're hindered in any way. But it will be a real benefit to know. We'll be using, it's actually called Simulink. So we'll be using Simulink, and a spin-off from that, you've got Simulink, spin-off from that is Simscape. From Simscape, you find Sim Multibody. And Sim Multibody is what we'll be using. This is a phenomenal bit of kit. I use it for material selection, mortar selection. I can check for efficiencies. I can check for output of mortars. And if I don't know what a motor is going to be, I can actually weight the whole system, and it will tell me what's the ideal motor for the job. You've obviously got to know about the behaviours of the motors, but it really does allow you to do that. So, with COMSOL, simulating with FEA, what we'll be looking to do is we'll be looking to, we'll be going through that real question of when you run it, how do you know it's something right? Where is the verification in it? Not validation, because validation is physically testing against the already calculated and simulated output. Closing that loop, if you will. In this, what we'll be doing is we'll be calculating out, and then we'll run a simulation to make sure that we've got some verification over the top of it. Is it right? Is it in that right direction? Can we actually show that it's doing the right thing? So what we'll be doing with that is we'll be using a little bit of variables. So in COMSOL, what we're able to do is create models by variable. So we can say A is equal to 20 millimeters. And what it'll do is generate components around that. At the moment, the only reason that we're not doing COMSOL first thing is we've gone on to the new remote server. And on the new remote server, what we're attempting to do is get everything on there, and it's just taking so much longer than we thought it would. So what we're going to start with this year is we're going to start with Matlab. And then into semester 2 we're going to start looking at COMSOL. So with the simulation on COMSOL, what it's able to do is you can look at a system from the bike frame. If you look at the bike frame, it's looking at weighting to the back, but it's centering the attention around where the back end is actually sitting. Now this simulation was produced by somebody from COMSOL, and they were looking at trick riders. I don't know if you call them trick riders, or that sounds like an odd name, but it was looking at people who do like stunt riding, I should say. And
looks like a jump frame.
Thank God somebody filled me in on that one. Because, I knew it. It's like, I don't know who knows Ed Sanderson, but he actually does that type of stuff. So he owns one of these anyway. And he would have shot me, just knowing that I got all that wrong. But they were literally looking at that initial impact, and they were looking at the arms and how well it could cope. Now we can do stuff like that. If you look at the bottom right, where you've got the rotor blades, this is really sweet. If you are into wind turbines, if you are into any type of rotor system, wind turbines is really good with this, because what it allows you to do is apply your variance to it, so you can have a wind force against the front of it, and as it hits it, you can get the vibration straight from it as the blades are actually spinning, and you can look at possible points of fatigue depending on the material that you're using. And then because this is my PhD was in this, so I do rabbit on way too much about it. What you can do with it once you've got it is you can then pass this through to Sim Multibody and actually run this on the electronic side as well. So you can look at how energy efficient this is based on the results you're getting from this. And this is all software that we have on the system already. it's a mountain of different stuff that you can do. Now you'll notice at the bottom left, you've got what looks to be like a bent piece of metal or something. Basically, it's fabric. This software, if we're using surfaces, this software will allow you to recreate any fabrics and the interface of fabrics. Fabrics are a really hot topic, really hot topic, because if you think of what I was talking about before with the stiffness matrices, and you go to something like fabric, you come away and go, wow, so does that mean that the fabric can adapt, and how does the stiffness matrices work? If you think of that K value, there is a technique known as soft springs. I know this gets things very complicated. And this allows springs to react more elasticated. And then that elastication value is what you're looking to try and apply into something like a fabric like that. So again, we will go through that. We will start to have appreciations of that. I do want to do something that's called hyperelasticity. With hyperelasticity, this is the deformation of rubbers. So things like nitriles, and so nitrile rubber is a very commonly used rubber for things like O-rings, different types of applications all over. You will find it everywhere, but it's incredibly strong stuff. But it does its job incredibly well as well. And what we're going to do is study that, look at its effect. When it comes to sim multibody, now these are actually quite old. I should have updated them pictures. They don't do it justice, I won't lie. So what you're looking at the back is we've got a KTM 525 engine that I actually built for my PhD. The reason I say it looks old is that is when multibody was brutally difficult to use. Brutal, I swear to God. And with multibody, you've got to build it, you've got to understand where it's all going, but with the new versions you can actually pluck out specific points. Now that engine I was able to run, well, it would run in real time. I was able to apply lubrication. I was even, now I know you lot will just go, yeah, so I was able to apply the wear coefficient, and it will predict how much material was being lost at each cycle. Don't get me wrong, I know it was practically atomic sizes, but I was able to monitor the level of wear that was occurring, and because I was able to do that, I was able to also model collections of material where you'll end up with, like, say, large asperities, large chunks, and what it would do is give me an overall for efficiency, so I could actually predict how well that engine would operate when it was running in race conditions. Now I'm not saying what we're going to do is do that. What I'm saying is we're going to set up what my first versions of this engine were. So this was predicting the reciprocating mass. I only laugh because everybody who sat Matt's first year module and everybody who sat Matt's second assignment on the reciprocating mass, you're looking at some of the first things I used to actually get that data sets together. I was able to move data around, I was able to change the position of the piston and actually generate you data which was incredibly difficult to dissect. Hence why the assignment was confusing and it left you a bit annoyed. That's what I was doing, trying to get you thinking. I know it's horrible for first year students, but I found it quite entertaining. When I shouldn't laugh. Also at the front of it you can see a bouncing ball. Now I know a lot of people will go, well, so what? It's a bouncing ball. The contact mechanics of elasticated materials against flat materials drops in lots and lots of problems. The first one, the biggest one, is known as the Hertzian problem, where if you think, right, when I was talking about nodes, when I was talking about how this was set out, how we've got these, because I know some of you have done some FEA already, which is great, but if you've got these nodes in between it, if you have a round surface touching a flat surface, what if these nodes are out? When you have these nodes that are out, you can lead to what they call penetration. I know it sounds like some sort of filth. It really does, but it can lead to a penetration. And what it actually means is when you literally look at the material, you'll see that material's gone through to the other side, even though the system says no, everything's fine. It's not fine. However, if that penetration becomes too large, what the system becomes is unstable. As it becomes unstable, what it'll actually do is it'll allow nodes to pass each other. And that is where we've got to try and tune it. Now, in Matlab, in Sim Multibody, anybody who's actually used Simulink, anybody who's actually used Matlab before, you'll know you can model equations. Somebody give you an equation, you run a cycle through. And once you've modelled that equation, what you can actually do is simulate that equation. Now, take that idea of coding that simple equation. For those who've never done it before, we are going to do a little bit, by the way, because I want those who don't know about it to be aware of it. Those who've done it before, I'm going to give you some extra bits as well, because I want everybody to be aware of modelling equations. It's really, really useful technique, and it really puts Matlab in a true shiny position, because it just allows you to do so much. Now, coming back to the bouncing ball, there is a lot of predefined equations that we know already. We know the coefficient of restitution. Now, the coefficient of restitution, the bounciness. If you had a coefficient, let me get this right, if you had a coefficient of 1 and you drop the bouncy ball, it will probably bounce off the planet. It's very bouncy. Some of you may know it as flubber. I don't know if that's too old for you, but with that, what we're able to do is predict that behaviour. You build that into it. If you know the speed of something by F is equal to ma, what you're in a position of is you've actually just got a visual representation telling you how something's moving, but then you're actually getting out the output. So this is just a visual representation of it moving. But what we're going to do is go that extra bit. Rather than just on bouncing balls, we are going to do robotic assembly arms. We're going to look at an engine. We're going to look at gearboxes. Gearboxes are very interesting, really interesting. Because the way teeth interact with each other, it's not straightforward. Teeth, if they're dry, they will start to have material transfer. If they're lubricated, they can slip. There is that sweet spot, if you will. And we can actually model that. We can look at them efficiencies. We can do all sorts to it. So it's crazy what we can do. Before I ram it on anyway, is there any questions about this, by the way? Awesome. What I'm going to do once we finish this presentation is I want to just make sure everybody's set up for Matlab. So please don't feel panicked about, oh my god, is it on, is it not? I just want to make sure everybody's pretty much set up. And then once everybody's got the downloads and everybody's all running, I can explain a little bit further about what the direction and how this is going to work. And the bit of a tutorial that I have for today. The way that these sessions are going to work, by the way, on Wednesdays, I'm probably going to do Matlab Sim Multibody. On Thursdays, I'm probably going to use SolidWorks Motion, studying the same problem. Now, the reason I've done this is purely because we've got a recording. I'm here to actually be spoken to. Anytime I'm here to be spoken to, not a problem at all. But what I wanted to do is remove this need for you to sit there and just listen to what I'm doing. I wanted you to be able to choose which way you wanted to go with it. So for the dynamic side, we're going to use Matlab Multibody. I would strongly recommend you stay with Multibody, but it's going to be down to you. And we're also going to use SolidWorks Motion and look at using that as a dynamic system. So the bouncing ball, for example, we're going to study why it's really problematic from the start, actually in SolidWorks. But it allows you to understand the limits. As John Calderbank, Graham's dad, once told me when we started teaching this topic, it's alright telling somebody that this simulation will answer everything, but you're best to know the limitations. And you are best to know the limitations, because when you understand the limitations, you know how far you can really push this. So, finally, now I'm aware that I've got some sit-ins. So what I mean by sit-ins, I've got some masters group sit-ins who are just looking at developing some more of their own skill sets on FEA and dynamics. So I know you guys won't be sitting the actual assignments. So the first assignment, because I'm going to flip this round, because I want this FEA to be mint. I want it to be well set up and well defined. And at the minute, we're still trying to finalise how it's all going to be set up correctly. What I'm going to do is we're actually going to run multi-body first. So we're going to run with the assignment 2 first. Doesn't mess things up, it just means that we're doing dynamics first, and then we're going to go to FEA into semester 2. The weightings, I should tell you, the dynamics one, I do ask a lot. I want to know a lot. I want you to really have a clear understanding about a lot. Sorry, that's my phone. And when it comes to FEA, I actually get you to write what will be a journal article. When it comes to dynamics, I get you to submit even the model that you've done. In the FEA, I want you to just talk about your simulation model. Don't need the model itself. I need to make sure that all the detail that you've done is in the work. So that's how that's going to work. As I said, in the assignment, sorry, we'll be doing 55% for assignment 2 and 45% for assignment 1. So, give me 2 seconds. I just need to nip to the loo. Back on again. So, I think I've got some questions rolling in. Have I got questions rolling in? Oh, I've got questions rolling in. Good question. Again, I won't read out who said it, but the question is, so is this module going to be part maths and part simulation? What I would say is we are doing the maths. We do need to do the maths to verify. We are not centering heavily on the maths because one thing I personally believe is maths is important, extremely important, but it is a tool to allow us to find solutions to what we're doing. So I'm not doing heavy maths on it, but we will be centering our attentions onto a solution that we're getting. So I think the hardest question will be yes, it will be part maths, part simulation. If anything, it will be more of sections of maths and mainly simulation. I want to centre the attentions on what we're looking at. So we have that, we kind of look at something and go, that's great, but what the hell is it? And what we're going to do is actually pull that, and we're going to dive deeper into that. So, as I said, what I wanted to do is quickly set you guys up for using Matlab. So first things first, if you guys don't know, this allows me to check to make sure it's there as well, because as I said, teething issues can be massive. So on your Blackboard, just going to log in. On MP3672, let me just make sure it's there because it might not be, knowing me. It is there, thank God. On SolidWorks and Matlab download. You'll find all the information that you need for installation. Information for installation. Thought I didn't know it. When it comes to the SolidWorks side, if you are wanting to follow me with the SolidWorks tutorial sets, that is what I'll be doing on Thursdays. That key there is the one that I use to install it on my system. It seems to be working alright. Please let me know if you have any issues and I'll try and resolve it. I had loads of things going on. The other thing I need to stress, anybody who had this issue last year, God, what a nightmare. Dassault decided to make sure that they could restrict every key value that you actually got. It became a bit of a shock because they didn't always do that. And last year nobody knew about it, so everybody just uninstalled their SolidWorks and then just reinstalled. No one knew that it was actually keeping a log on your MAC address. So when you go to uninstalling it, be sure to deactivate your old license. Somebody told me that it's now automated on Dassault, but how many times, I mean the amount of times I've come across stuff and it's automatically, it's automated, you kind of go, not convinced, don't believe it. So I would always say manually deactivate. For anybody who wants to know, it's in the, when you're in SolidWorks, actually in the software, go to help and you'll see deactivate license. Just deactivate it, even though it says it's going to do it automatically, still not convinced. Right, so onto the Matlab. Now with Matlab, I love this, really do. So on your student, go to the downloader. So I'm just going to go to the account. Now give it a minute. Give it a minute. So when we come up to Matlab, you'll see me with my daft picture. Life's too serious. Best to take funny pictures. Right, so you'll see that I've got individual and concurrent. Now I think, let me just check on the paperwork that I gave you. So click license and then associated licenses and download now. Okay, so we're going to go to, they're actually the same license, so really I can just click on any. So I'll just go on individual. Now I've already installed this on my system, so it's not going to. You know, looks and was like, yeah, but you've already got it. What are you doing? I do already have it, so so I can go to my download installer, and what you're wanting to make sure is that you have Sim Multibody and Simulink all on there. Under my products that I've got installed, I've installed everything. Should point out that the full installation of Matlab, when you buy it for one person, is £135,000. Each toolbox is worth, I think it's just short of £1,000. So it's not cheap kit at all. Simscape and Sim Multibody is what we really want. If you download it and you choose to install everything, you know, crack on. More and more experience the better. The other thing that you should know about Matlab is you will meet a million people who are Matlab experts. They go, oh yeah, I know how to do that. Yeah, I'm an expert. You only ever meet somebody who's more of an expertise within one particular area of Matlab. Matlab is a monstrous bit of kit. Anything you wanted to learn how to do, you can do it. I mean, I heard someone say to me once that Matlab will solve anything. All you've got to do is be smart enough to use it. Sounds a bit brutal, but very true. I've left that in there. That's not true. I'm actually using 2020A, which you can download. This is our activation key. Try and download it, get it installed. If you've downloaded it already and it's installed, fantastic. I am going to produce stuff based on that. 2 seconds. Have I got more questions? I don't think I have more questions. Oops, excuse me. Right, so let's have a look. Yeah, so these are all your installation processes, how to get it on and what you need to do with it. As I said, get onto Blackboard and download the paperwork and then just follow the paperwork through to get that installed. The other thing I needed to tell you about as well, what I am doing is I will be taking a schedule. A schedule and attendance. Now, as I take the attendance, what it will do is it will take a snapshot of everybody who is on at that particular point. It takes a snapshot. I'm just going to pause my. Let me just pause that. It takes a snapshot of everybody who has logged in and logged out. It will tell me when someone came in and when someone went out. I've been asked to do this to make sure that I have an attendance throughout the week. So what I'm going to say is everybody's welcome to both sessions. I know what you're going to say, can the groups be updated? If we updated all the groups like that, your timetable would just look chaotic. You are welcome to both sessions. The other thing is for those of you who don't know about this, on Blackboard, normally what I do on my, let me just get to the beginning. Normally on Blackboard, what I will do on my module materials, I normally give a link. This link is going to be recording, so this recording, for example, is going to be on the link. This recording will be on the module materials, so the live sessions, and just to let you know, in the live sessions, you've got the Wednesday link and the Thursday link, so anybody's more than welcome to come to it. The recording from today will be uploaded onto Blackboard. Tomorrow's session, I will be examining more of SolidWorks motion. This session, I want to start introducing you to the use of Matlab and navigating your way around Matlab and getting used to its interface. I don't think I've missed anything there. If I do miss, I will dive back just because there's so much sometimes to remember. So again, I do download an attendance list. And now I've just taken a snapshot of everybody who is here. So, Matlab. Functions of Matlab. Again, this, for those of you who've done this quite a bit, apologies. This is just purely because I want everybody to be aware of the interface itself. So, around 10 years ago, Matlab went down the road of like the Excel approach, where you've got the top toolbar. Matlab didn't always have this and did not have these tabs neither. It's a new format that's relatively new to it. I say new, but I suppose not really that new. In the Matlab window, we've got the command process, so I can say A is equal to 10, B is equal to 20, and C is equal to A plus B. So it's a quick way of defining particular elements to it. So if you look here, we've got that command window and I can easily add things to in there. I can add things particularly there. And when I'm adding things in, a beauty of this is it's assigning me variables already. So I could say if I was using a variable of TI, I could make that 2 to the power of 10. And instantly it's applied to it. Now, knowing about these variables at this point doesn't seem really put any benefit to it at all. However, we are going to be using, when we're using multibody, this function here will be extremely valuable because we can actually run variables from here that will control the simulation. If there is changes in that simulation, it allows us to have that flexibility to know where we're going. So let me just empty that. And 2 seconds. Yeah, right. I've had a question about ownership of laptops and PCs. The best thing I can say with this is I will have to ask about this. I don't think it is, but I can actually find out. So it's about not owning a PC or a laptop, and is the campus still available for the facilities. At the minute, we've been told to keep everybody well aware as much as humanly possible. When it comes to the library, for example, I do need to find out exactly how much access is there to it. It's purely because of just COVID and the rise in COVID, especially these particular areas as well. we're trying to cap as much as possible with the ability for this to be transmitted. And the last thing we want anybody to do is to become infected with the virus, hence why I will need to find out to get you a straight answer for your question. So that's the best thing I can say to you on that, but I will get back to you on that. Right, so moving on to the left, we have the current folder location. If you're starting to build large simulation structures, you need to be able to tell the system where all these models will sit, because the way that this process works is you have an address. So if I navigate my way through to 3672 onto my Dynamics and then click select folder, I sit inside of here. Now if I want to use particular files, folders, things like that, what I need to do is I need to tell the system where my models are. So let's have a look. Let me have a look at one particular thing that we'll be looking at. Let's take a look at the gearbox. I don't know what I've got in there, but let me take a look. So you see here, I've got two teeth. Two sets of teeth. I've got two models that are step models. What this system will do is it will read directly, but it needs to know where my file types are coming from. I'll let that load because I'm going to show you that in just a second. The bottom left here we have the model viewer. It will give me an insight as to what's on there, what's being used. Now you'll notice there it's taking a long time to load because Simulink is a separate software that runs actually with this system. What we're going to do for just a bit of a warm-up today is we're going to use a little bit of scripting and get used to using a little bit of scripting. I do need you to get Matlab installed for next week at least, just so that everybody's set up for it. If anybody's keen to follow me with the SolidWorks Motion example, get SolidWorks installed as well. Again, I'll be recording these, putting these on Blackboard. For anybody who wants to know, the only reason I don't use Microsoft Streams is the Wi-Fi signal. If the Wi-Fi signal drops, we get this bad signal in the recording, and I don't like that. I like it to be consistent all the way through, so I use an on-screen recorder. I then encode it and then I upload this and turn it into a link on YouTube, because I run an unlisted YouTube channel. This allows me to put the link on Blackboard and you can just click onto it and it will just allow for that to happen. So it's just so you're aware of that is what's going on. Right, so it's taking ages to load. So I'll keep going through here. So on the script, on the new script, we have live scripting, which I'd like to try and do this year, but we have an awful lot to cover. When we're on to new, on here, it's pretty much, because new script is a very quick way of being able to build it. We go Simulink model, which we will be using, not today I don't think. Here it comes. I'll just minimize that. We have Simulink model. New functions, live functions. We will try and cover as much of this as possible, but I do really want to focus all my attentions onto the more simulation side of what we're doing and the results that we're getting, so what we're really looking at. This is a typical example of what we will be doing. So let me just bring that back. Now, to let you know, I actually have geometry from SolidWorks, which was two different types of gears. Those of you who are very competent in modelling, you're welcome to build your own models. Those of you who are not the strongest, that is fine. I will give you models. This module is about the simulation, not the modelling. Never about the modelling, so it's more focused onto this. So what I'll do is I'm just going to show you something of this running. So if I run, come on. What this does now is it builds up the physics behind it. Now this is what we're going to be looking at. So if I spin this round, come on. Now these are typical 2 nylon bolt gears. Now it seems dead straightforward, but what we can do with that is we can look at coefficient of friction that interfaces here. We can look at the force that's been put out. Well, we can actually look at the torque, I should say, that's been put out by the motor, or the other way. If we know how much this takes to move and we put something in it to make it move, we can then look at what level of motor we would need to make that move. I know it's a simple example. I know it's a dead straightforward example. But there's a few key things in it that we're going to be really examining. And it's the use of models from the outside. So step models, things like that. And building up a real detailed example. So if you were doing something as a project like this, you can put in efficiencies. So you see here I'm just feeding it in with a signal. But if you knew exactly what the electrical signal was doing or what your energy efficiency was, you can actually feed that into the system and it will give you even more of a detailed output. The kit in this is phenomenally good. Let me go back to where I was up to. So a bit of a navigation through. We can import data, Excel, text files, anything that has data particular points to it, it will allow you to import it. Obviously Simulink, shortcut, set file paths. We will cover a bit of that because we may need to do it. I am looking to add some extra, I call it extracurricular bits to this module. I have been dying to actually do live data acquisition on Matlab for years. I've just never really had the opportunity to be able to do something like that, purely because there's just so much going on. So now we're online, this gives me the opportunity to be able to do something like that. Now what I do on my research, on my exoskeleton technology research, when we're doing live data acquisition on the body and it moving, if we're doing live data acquisition on muscular differences, we can actually read it directly from a human or from a target. I call them a target, but or the participant, which sounds even more cunning. Or sinister. What we can do is we can actually read that directly from an Arduino, from a Raspberry Pi, or we can issue commands from Matlab to an Arduino or a Raspberry Pi or anything like that. And what I'd like to do this year is take people through that, so adding hardware support packages. I'm probably going to add that in. It won't be anything specific to the module because the module I want to keep focused on that simulation side. This would be something extra because what we can do is run real life data sets, then simulate against it and make sure it's going to work. Another really cool element about this as well is as we're doing live data acquisition, let's say for argument's sake we're building a prosthetic. Let's say we're building a prosthetic arm. And what we want to do is make sure this arm is going to work like we think it's going to work. Because, you know, the mechanical design looks great, everything's cool, all the mechatronic elements that are going into it looks really good, but how do we know that it will function like we want it to? What we can actually do is get the participant, or yourself, attach electrodes to your arm, for example, and then you can make a fist. And as you're running this in multibody, what it will do is it will read that data and then push it through to your model in your simulation and actually give you a live update of the arm actually moving. Again, it's a little bit outside exactly what the remit of this module is, but it is a real benefit to know how to do it. So I am going to record some videos about that using cameras and then tracking that and then giving you that experience. But again, it's not what I'm assessing directly on, but it is just a real cool element. So if you're doing something like, let's say you've got an engine test, you're receiving live data from Ricardo Wave, Dyno, anything like that, and you want to feed that directly into an output from a new design for a drivetrain, you can actually do that. And you can take real data and see what happens. I have had one student once before who actually did that with Tony Broad's Shell Eco Marathon. He built a simulated version of the Shell Eco Marathon car with simulated weight of the driver, everything in it. What he wanted to do though is make sure that the way that the driver was in was a true representation. So he used live data from that driver and was able to match his simulation to the car's output to 10 to the minus, I think it was 15 meters. So the error between it was so small, It means he was almost absolutely bang on. And we think the one thing that is perfect in here that isn't perfect in the real world is the combustion process. Our combustion process was perfect and his was not, and it just added to that inconsistency. It was a phenomenal project, really, really good. So, moving on. Plots. We are going to be using plots. It allows us to extract stuff quickly. Having a plot and doing a plot that says a lot. A plot that says a lot. I tell you, I'm on fire this morning. If we have a plot that says a lot, what it allows you to be able to do is really relate what you're talking about. Last thing I want to see on an assignment is the blue line says yes and the red says no. That is, you laugh, but I've actually had that happen before. I've had people submit when they say the blue line goes upwards and the red line goes to the right, and you go, brilliant. They refer to the line being the output. The line isn't the output. The output, the line on a graph actually is just a representation of what something is. And that is what I'm looking for. I'm looking for the right terminologies to be used. I will be pointing you in the right direction as we're going through, but these are all incredibly important. So you may be the best simulator in the world, but if you can't relate it, you don't serve much purpose. When it comes to apps, I've had students... The apps is kind of like your app store for your phone. On your phone, you have all different outputs that you can use, and on the App Store, you download something and you use it. Now, Matlab do offer this as the same thing as well. If you design something and you think, yeah, this works really well, you can actually compile it as a single app, then pass it to Matlab, and if Matlab verify it and they're happy with it, what they'll actually do is put it out on their main server and people can buy it. I've had one student do that before with a dyno tester for damping. What he was looking at, he was working for, I forgot which race company he was working for, and they had the dyno for the car, and what he wanted to do was to be able to have an app that companies could install, and all they do is do the live data acquisition, and what it will do is simulate at the same time, give verification of what they're doing is the right thing, but they can also tune the output of the car on a simulated version and the real version. Now I know people like Leyland trucks, a lot of people don't realise how advanced Leyland trucks actually are and what they do. They're very advanced and quite ahead of their time in many ways, and they have been for many years. They've been doing that for a long time, but what this student wanted to do is he wanted to offer a simple app that you could use on Matlab and it just work. So you can do that, but your work needs to be, in lack of better words, tip-top. It needs to be the best. Finally, navigating through the world of Matlab, because, as I said, those of you who did this with Matt Stables, apologies, this will be a lot of repeat because I know that you guys have done it. The other thing I would strongly recommend you do is join Matlab File Exchange. This is the nerdiest thing you've ever seen in your life. It's awesome, and I won't hear anything else. But on this website, what it is it's just a collective of people who are looking at different stuff, and they're trying to model different things that are going on. You've got professors on here, you've got people who really wind each other up on here. But these are nice little starters. So if you are looking at, there is a nice example of a wind turbine built by one of the guys I met, who's now one of the engineers at Matlab. He built an entire turbine from the ground through to wind hitting the blades. If you do get a chance to see this, you should take a look. The sophistication on this work is phenomenal, but you can find it on here. What it allows you to do is take baseline and then change it. Matt, who's from this, not me, but Matt, he built this up, and he does freely say, use it as much as you like, but do not just basically take it and go, look at what we've done. You need to refine it and actually do it the correct way. But his is a baseline instruction, phenomenal. It is not straightforward to get working, but it is definitely worth looking at. Again, if you get a chance, please join this. It really helps you for further understanding about the software itself. The thing that's coming up now, though, is a lot of these are coming up is because of what I've been using. So you'll see there the Deep Learning Toolbox, and we've got NeuroSky things on here as well. So I have kit here, that I have kit literally on my shelf up here that will do EEG sensing, so I can read brain waves and things like that. But that's a different thing entirely. Right, so that is my overview as to the introduction to the interface itself. Again, I do appreciate that some of you have used this quite a bit before, but I also appreciate that some of you are brand new to this, and when you first look at Matlab you go, wow, that is so boring. But I promise you, underneath the hood, it's an incredibly powerful bit of kit. The other thing that I find really useful, on here, if you type something in, if you type a command in and you go, yeah, it worked, and then you forget what it was, one thing to remember is the command window is not just a command window. What it will do, if I push up with my arrow, what you can see here is former commands I was putting into it. I mean, it will go back. Now I leave my storage on for months. I think on the university system it only stores, I think, for about 2 weeks, but mine stores I think ever since I've had it installed. I think I think it's around a gig's worth of data going backwards, and then it will start to delete. So if you look there, in fact, if you look there, 3rd of the 3rd, 2017 is the last record that it's got, and it's still going backwards. What we're talking about, still going backwards. 9th of the 9th, 2016. So that gives you an idea of how long I've been using this. But I can track back, and it doesn't seem much, but when you're going through, you need to know these things. It really, really, really is a helping hand. So 2 seconds before we continue. Do we have any questions on this? Give me 2 seconds. What I'd like to do is to just do my first. I'd like to just go into my first particular example. These are notes that I will be uploading, so don't worry too much about if you've not got this installed. Even if it's not installed, I would genuinely recommend that you just get used to it and have a go at doing this. So let me just find a nice example. Right, where are we? Oops. I'm just checking through my notes to make sure I get the right one. Okay, yes, I think I found the right one. Right, so a first order system. This is a nice example. A first order system would be a door shutting. Now if you imagine a door shutting, I'm going to roll up and down on this just because it's a nice example and I need you to be aware of what the hell it is I'm talking about. So if you imagine a door shutting, this is pretty much how you'd imagine it shutting. You've got the time that it's moved and you've got the displacement that it's made. So you've got over 0 and over in hours, that's a door shutting very, very slowly, clearly. But if you imagine it shutting, it will rise, and then it comes to a steady state to come to rest. Now that typical idea is because there is a spring and a damper sitting in it. The spring, as most of you will well know, the spring is an energy storage methodology. So if I convert energy to it, so if I pull it or if I compress it, I can put energy and it will be stored within it. Then once it's released, it will try to return back to its normal state. However, if we want to control that state of return, we can put in a damper. Now that damper will dissipate that energy, so I can choose how it's been passed between them 2 points as it's running. A typical drawing for it would look like that. Now the equation for that is simply y position is equal to its former position plus 1. So that's what my next position will be. So the present Y position is multiplied by h of my time step, dy by dt. So my acceleration equation, and then by the number of where I was sitting. So what we're going to do is we're going to build that as an equation. Now as an output, that is a nice way of it showing. So if you look here, I've got my y2. My y2 is equal to y1 plus my h by dy by dt. So if you look here, if we consider this to be time and the variable, our initial position of y sits here. So what we do is we predict the time, and we also predict its position. Literally going back to high school mathematics, really. And what we're able to do is to give our next initial state of position sitting here. The issue is if you think about this is a iterative process. Really what it's going to give me is quite a truncated response. If you look here, we've got this nice smooth response because that's what we'd truly be looking for. This is a similar issue to what we'll face when we're meshing. This resolution between these two and the speed that it's moving allows us either a lot of accuracy or minimal amounts of accuracy. Now there's methods that we know as convergence that we can do, but first things first, let's script this process. Again, let me go on to the notes, because what I want to do is free up these notes. So those of you who are very confident, because I know there's a few of you who are very confident in this, I want you guys to be ready to go with that. Right. Oh, that is awkward. All my notes are still freed up entirety, so I don't want to do that just yet. So I will have to free that up after this session, if you don't mind. We will work through that way, and we'll do it that way. Just because I don't want to free everything up as of yet, just because I want some mysteriousness to it. Right. So for those of you who don't know with scripting, what I'm going to do is I'm just going to navigate myself to the right spot in my notes. Just want to make sure I'm in the right spot. Is that the one? Yes, that's the one. Right. So again, anybody who's not used to coding, what I've done is just move to the right notes that I'm looking at here. So I've got lots that I've been working on, and I just want to make sure that I got the right amounts that I mean. Right. So first things first, I'm going to go new, and I'm going to go script. Right, so what we need to do is we're going to operate from these nodes. Let's have a look. So from these nodes in particular, we've got our initial equation of state, which is tau, which is y is plus tau of dy by dt, which is equal to the static sensitivity and the initial position. So, oh, there we go. That's what I was looking to show you. So, the static sensitivity is what's known as the gain. For those of you who are very confident in understanding the gain, it's output over input. It's what you put in, you get out. And the static sensitivity in a single order system, we normally set this to 1, because what we're doing is we're presuming that the state of the spring and the damper is perfect. We're not going to put any changes into that. When it comes to U, obviously this is referring to equations of motion. So U is our initial input. T is the time, well, tau I should say. Tau is the time constant. And C being our damping, and K being our spring stiffness. Tau is actually a mechanical relation between the two. So the time constant actually refers to our spring stiffness and our damping coefficient. When we come back, what we can see here is in fact, let's start building this up and putting this into position, or else this is going to get very confusing for you all. So, what I know from them notes then, I'm just going to make some space. I'm going to say C is my damping coefficient, so I'm going to C is equal to 1. And in any good coding, should always put on a comment. So I've gone percentage damping. Don't forget, these are to allow you to. I wonder if I can make this bigger. Is this too? I don't know if anybody can answer me, but can you see the size of these, or do you want me to try and make it bigger?
If you could make it a little bit bigger.
Yeah. Okay. 2 seconds. Because one thing that really dawned on me then is even I was starting to squint. Is that gonna? No. Right, sorry, 1 minute. So I'm sure it was in here, so where are we? Fonts. Can I do it? Wow, that's done it, right. So I knew it was there somewhere, so if I come back, that's what we got. Again, if it does start to look a little bit too small, please let me know, I'll make it bigger. Right, so we're going to go spring stiffness. I'm going to free these notes up. The only reason I've not freed them up is I just looked, and all the rest of the notes from the year are all also attached on there. So I just want to make sure that I can systematically release them without you going, oh my god, what the hell are we looking at? So the spring stiffness. S is equal to 1. Now this is that static sensitivity, so to just relate you back to these notes, this is the static sensitivity, again more commonly known as the gain. The trouble is in different books, so the Mechanical Engineer's Handbook, if you look in there it refers to static sensitivity, then if you look at a more second, third or fourth or fifth order system, it refers to it as gain. And it can be very confusing, so I do want to keep talking about that. So the static sensitivity, if I can even spell it right. We've then got U, which is our initial input of this system. So in our case, what we're saying is we're going to put in our first initial force. Now, I think, rather than thinking of this as a door, let's not think this as a door. Let's just think of it as it is, as the spring and the damper, and then we're going to provide an input and we're predicting that next initial state. So I'll input that as 5. Whoops, I'll input that as 5. Tabbing it in again. Again, I'm just going to put on my my percentage sign. I'm going to go U is equal to, I'll just call it input. Should be really initial input, but knowing me, I'll spell it wrong. Y in this state, if we're just referring to, because I think it's easier just to refer to this way. If we're just referring to where that Y sits at the very first point, and I mean the very, very first point, what we're actually doing is we're saying this has to be 0. It's basically saying at the very first time you start to simulate, where is it? And it's obviously 0. I have, I shouldn't laugh, but I have had some students before who were trying to tell me that, no, it's moving. No, I mean 0 seconds, where is it? So it's 0 as far as a positional state. So we'll go first pause. Now that all important time constant, our tau. Now you can put symbols in, but I'd rather just type it. It'll just make life so much easier. Tau in this case now is dead easy. C over K. Let's just close that. Oh, I don't like that. Look at that. call it time constant. What I'm just going to do is tab this along as well. I know it looks really annoying, trust me. When it loses that line, the worst thing is with Matlab, if you end up, you might end up with OCD. Just because you run it, you go, oh, that looks a lot more tidy. So it needs to be well presented. Presenting stuff well is very important. So, we now have H. Now, what's my best word to describe? I keep referring back to my notes just because I want H to be well represented. So I just want to make sure I'm referring to H in the right way. Oh good, I don't think I referred to it. Okay, so with H it refers to the time step and its initial points for it. So what I'm going to do is say, I know this sounds a bit daft, we're going to say where is time starting from. I'm going to say time is going to start from 0. You'll see why in a minute. And I've got time step. And then I. Now the reason I'm using I is I'm going to use this as an increment tool. This allows me to increment along and keep incrementing that way. Now if anybody's curious as to why I'm using H in the way that I'm using H, this is purely because I'm going to increment this using a while loop. H is starting at 0 because I'm going to use this and literally say from 0 through to a time, keep running to get a solution, and it will increment that way. There is other ways of doing it, and I'm sure Matt, I'm going to ask Matt what he'd like to see as well, just to see what his ways will be, which would be interesting. So I'll call this my increment. Well, I'll just call it in. So again, what I'm now wanting to do is to start with the very first thing. So if you look here at the way this equation behaves, the first step of this is I need to have my distance over time, my dy by dt. And if you look, what it's actually referring to is where it's moved, and then we're trying to equate the next points of position. So our first thing that we really do need to calculate is our dy by dt. So if I scroll to just find that solution, according to this, it is static sensitivity multiplied by my initial input minus my position of y all over tau. Again, I will be hang on a second. I've got people trying to take over the presentation. I like that. No, not happening. I've restricted a lot of access, so it won't work. Yesterday it wasn't working at all. I had students kicking each other out of class, which was a nightmare. But yes, I spoke to Tony last night. So back to the point. So I'm going to go while. Now the reason I'm doing this is, again, I'm going to give a starting point and I'm going to run it through a time period. So I'm going to go while h is less than 1, because I'm going to increment a very small time step. What we'll do is play around with that to look at larger and smaller increments. So while that's going on, do this. So I'm going to say my dy by dt is going to be equal to, comma, argument. Now the reason I do that is that this is going to stay inside its own equational state, because don't forget this was static sensitivity multiplied by initial input minus y all divided by tau. So the way to see this is the same way of that Excel interfaces as well. So I say s is multiplied by u, close the argument, minus y all divided by tau. And that is my first step. again, as I've said, some of you will have done this before. I just want everybody to be aware of this as a tool. So I'll go y is equal to y plus h multiplied by dy by dt. See what this, obviously what dy by dt will give me is my velocity, which is extremely useful, as you'll all know. So now what I need to do, if I run this, when I run Matlab, it will create a single spot. It will create a single piece. It will create one initial output. So if I just say A is equal to 1, what this system does is, if I double click into here, what this system does is it creates this cell as a usable cell. If I don't tell this system to register a new value all the way through, what it will do is just overwrite the same cell again and again and again. It's incredibly frustrating if you're wanting to get live data sets, if you're wanting to record everything that's going on. So what we're going to do is actually increment that. So I'm going to say f, now this is just me making a variable up, is equal to I. Now what this is going to do now is, because it's equal to I, it's going to grab that increment value. That increment value when it starts is at 1. So what this means is that in the variable f1 in row 1, column 1, it's now equal to my dy by dt. Close out. And what it will do is it will drag out that particular value. I'm just thinking, what am I doing? I'm putting that in the wrong one. So I actually want it to be equal to y. Apologies. So that will give me my initial outputs. So my positional output. Then I'm going to plot my velocity. My velocity is going to be the same thing. So I'm going to say y is equal to row 1, column 1. Now this is going to be equal to dy by dt. Then t, because what I want to be able to do is plot my time, how long this has taken, or else what it will do is it will just give me random iterations, and I don't know how long these things have taken to move. With this I can predict how the spring and the damper have behaved and how it's responded as we've gone through. So t is equal to I. Apologies. I for row 1, column 1, close that, is equal to h, and then close, and then that brings out that as well. Now, once that's run through, h is now running at 0. It needs a reason to start incrementing, so I'm going to say h is equal to h plus 0.01, and this becomes my time incrementation. So I'm running at 0.01 as a time increment. Then what it needs is it needs to know that it's moving down the row when it's recording. So I'm going to say I is equal to I plus 1. And then I'm going to type end. This then builds that initial run. So this is the whole equation run through as a simulation like this. Now I do have the Excel example. I'm going to open up the Excel example because I want you to see the alternate option to doing it in Excel. And the reason that we'll do something as simple as this. So first things first, I'm going to save it. Matlab will insist on that you save in because it's aware of that things can go horribly wrong. So I'm just going to call this first order because this is a first order equation. And I'll call this SD for spring damper. What I should point out as well, no symbols, no spaces in Matlab at all. If you do, it'll just come back and say can't save it. It will not allow you to do it. You can do, I know in fact, I lie, you can do symbols but no spaces. If you want to have a space in there, do underscore. Underscore is acceptable. So if I do that, Now, if you followed me through, what I'm going to do is I'm just going to hit run. So if I now go onto here and then hit run, it asks me, I found a new location. I'm not sure if you want to use it. Do you want to add the path? For this, I'll just add it. I'll just add it for the minute. And what we see now is we've got these outputs. We've got our positional states. Now, if we look here for T, if we look here for F, and I should have vel here for velocity, what you can see now is we've actually got our outputs. So if I click onto here and then go here and then plot, simulate. I mean on to plot, and that's an initial output. That's so cool, I like that. And that's initially what I'm getting from that output. If I go to dy by dt, oh sorry, if I go to here and then go plot, see here we've got this rise and then this settling here. Now it doesn't really tell us much, not yet. There's still a few things that we really need to do to plot it correctly. You look at these increments, we don't know if that's in time, we don't know what that really is. So what I'm going to do is I will plot that. So I'm just going to say plot T by F. Now what we've got is a particular time that it's moved. We know that the rise time between here to here is at 0.5 seconds. So the response of the spring is quite quick. If we look here, you can see the steady state where it rises and then really starts to build up. These points here is tuning for the actual spring itself. It means that the damper is probably quite strong, and that the spring stiffness is relatively small in relation. So if you look at the spring stiffness to the damper, the relation between them is quite concurrent. You know, the damper is incredibly powerful in relative to the spring, so we can change that to see what's going to happen. We can do that in just a minute, which we will. The only thing is if I took this now and put it into a plot, it's not intuitive, doesn't really tell me much. I mean, if I really look at it and go through it, I can extract it, but if you want somebody to read your work and really take pride in what you're doing, you need to really spell out what it is that you're looking at. So what we're going to do is just come back and we're going to build up a plot that looks a little bit more sophisticated than what we've actually got. Now, apologies. What I'm going to do is create a system that's called the subplot. This is actually going to plot two graphs on the same plot relative to each other. So some of you may have seen this before. It's two separate plots and they look, well, in fact, let's build a plot up first, let's label it, both plots, and then let's look at creating a subplot to put them into one. So I'll say plot T by F, close this. Then what I'm going to do is I'm going to go title. Now this is purely because I want to tell the system that I want to title it, call it position. Close it, close, and I want to actually name the X label. So the X label in this case is my X label as it sounds. So I'll set my X label, open brackets, onto comments, we're going to go time. In this case we know it's equal to seconds because that's how we were building it. Then we go Y, Y label, again we open that up. We go to comments, and on our Y label we're going to say displacement. Whoops, displace. You know, racing and trying to look sophisticated. And we're going to run in meters because all of his points are coming out in meters, and then we're going to close that. And then let's run it again. Now, if you notice, this is something that's a bit frustrating. You see here. The values are still here. if I run it, what the system does is it looks at these values and goes, oh no, it's all different. So if I run it, it will have a major meltdown. It'll have a bit of a crash. So I'm going to clear it. However, I don't want to have to keep doing that every time I'm running it. I want it to be a slick running simulation. So what I actually do here is I'm simply going to clear the most important elements about this. So I'm going to clear my F, whoops, and I'm also going to clear...
Map.
Yeah, go on.
I know it's only a label, but you've still spelt displacement wrong.
Oh! No, that's how I meant to spell it. No, it isn't. I totally spelled that wrong. Yeah. Thank you for that, because that would have been very, very awkward. Yes, I did. Again, that was me rushing, trying to look cool. Didn't do that very well at all. Yeah, thanks for that, Hazel. Right, so I've got my label in, and I've made my... I've put my spelling right, so apologies for that. If I come back and I've cleared my F, I'm going to run it again. And what it will do now is it will bring that title in. I can change my... I can actually move that bloody thing. Oh, damn it. I keep seeing the give presentation permissions, and it's really annoying. I can change these now. I can change fonts if I wish. I can change all sorts with this. Again, we've got that rise between it. The positional state. I mean, arguably, does position really need to be there? It does if I'm going to do a subplot to actually have it on there. But that rise to about 0.5 seconds, and we look at the behaviour. This would be, the best way I could describe the way that this behaves is, you know when you have a door that moves quickly, it comes into its steady state and then slows down for it to close. That's a similar type of behaviour that we'll get, but this initial response from it kind of shows that that momentum does take its time to build around the damper, because the damper perhaps is a little too strong. So what we could do is drop that damper strength and then look at its behaviour. One thing I'm aware of though is this is just position. This is just where it's moved. I don't really know how quick it's moved, and that's really where I want to go next. I want to plot the dy by dt. I want to plot that velocity, and I just want to see how quick this thing has moved. So what I'll do again is I'm just going to type figure. And I'm going to, just because I'm being lazy, and I'm going to bring in my velocity, and I'm going to remove that, call that velocity. And it's in meters per second. In fact, let me just pop that out. I just want to see what it's going to give me. So if I run that, I'll get rid of that. Then run it again. Holy shit balls! It moves relatively quick. If you look at the 2.5 meters per second. Oh, let me put. I've not put my units on there. So meters. It moves at 2.5 meters per second. So between that, if we're looking at half a second, this is moving incredibly quick. But you look at the way it's returning back here, that velocity is really controlled. Now, if we use things like on the stats toolbox to actually give us a line down here, it will give us the maximum points that it actually gets to its quickest speeds. But if you look where the tail end of this occurs, it's a large tail end. This really does show that the damper is actually doing an incredibly good job with this. The thing is when you're designing these, or when you're trying to apply these, the application will dictate what you're doing. So I'm going to put them together. The only reason I want to put them together is I really want to start tuning that and looking at what each piece of this does and how it behaves. So what I'll do is I'm going to type subplot, and I'm going to go 2. So what this will do is this will allow me to put in row 2 by 1 on its position 1. So this tells me that there'll 2 be on there with 1 column, and I'm using the first one within all of that. So I'm going to close that, and just because it's important, I'm just going to tab that along, and then I'm going to repeat this process again down here. I want to now stop these two from being separate. I just want to look at these as an overall, and then run again. So I'm going to hit save and then run. Oh, because I was rushing again. So if you look here now, I'm going to say my second one in the 2, then run it. There we go. So this now allows us to look at where it sits and the speed it moves. So what we'll do is let's tune it. Now we've got this running, we can do pretty much what we want with it. To come back to these notes, this is what I've been referring to here. Now there is an extra bit to this which I don't want to have too much complication at the minute, just because I'm aware, as I said, I'm aware there's a lot of you who have done this before, but a lot of you who have not, and I just want you to see this. Those of you who've done this before, I challenge you to modelling the what they call the exact method. Now this is our normal way is for the exponential method, but this way is an overall method, and it's Euler's techniques, or Euler, or whichever way you want to say his name. I'm going to free them notes up in just a second, by the way. So with the damper, with the damper, if I drop that damper and bring it down to 0.9, because I'm clearing F at the start, this should overwrite my plot. So if you look now, we had a quicker response. And this is purely because if I bring that damper right down to something crazy, so it'll go way beneath the spring stiffness where it will struggle to hold it steady. You look, now we've gone up to 6. So now the spring takes over, the spring's energy is able to dissipate quicker, and the speed in its response is a lot quicker in comparison. Really, I mean, the length of all this, I could perhaps drop my recording down. So if you look here, I'm running until it gets to 1. So if I wanted to, I could say just run it to 0.5, then run it again. It wasn't happy with me doing something then. I'll check that in a second. I'll bring that back to 1. I wasn't sure what he was happy with me doing then. However, if I now start to match these two, so if I bring that up to a steady state where they're matched, what we end up with is where, if you can look, I don't know if that's going to let me scroll around, we'll be able to see. You're almost getting almost an overshoot on that first order. When you hit that steady state behaviour, it oh, that's not worked out well at all. When you hit that steady state behaviour, it will give you a slight overshoot. But if we go back to the spring stiffness and then start to incur a greater spring, obviously what you're going to get is the spring's ability will slam shut. Based on that spring stiffness and based on the behaviours and our input that we've got, you're going to get that overall displacement, obviously, because I've given an initial input. However, the way that the spring responds, based on the strength it's getting, can become quicker, because what I'm doing is I'm just encouraging a greater strength. So again, if you just run it, it will go massively out of control. And as a bit of kit, using something like this is really useful, because it allows you to tune for something simple like a first order system in this way. Right, so has anybody any questions on this? Right, what I'm going to do is I'm just going to free up them notes now. 2 seconds. I should point out this is the first and the last time that we will be spending a lot of time scripting, because my real focus really is on Simulink and using Simulink for modelling of equation and also running it as a simulation tool. 2 seconds. Right, so for anybody who's wanting further notes, on Blackboard at the moment what you'll find is Matlab and Simulink notes. On there are 2 examples. Whoops, there's actually a third thing there I've added, I forgot to turn it off. So on there now you've actually got 2, you've got the first order and the second order system. So under the second order system, again these are just notes which give you an example of how this is equated. To show you how this runs as a simulation in Excel, it's quite a bit different. Right, so now the reason that we run, that I personally like to just script a process if we're doing something like this. To script it is so much easier, because if you're looking to run this in something like Excel, because this is an iterative process, it can be very time consuming. So if I bring this back across, this is an assignment that we used to run quite a few years ago. Now the dy by dt, which we coded from scratch, this will run, well it's actually not running much in this example, but this can run for hundreds and thousands of lines, and this is just a very quick overall example to show students how this works. But what you've essentially got to do is iteratively run this through again and again and again, and you cannot end up between 60 to 70,000 lines in one single simulation hit. It just depends how accurate you make this. Now what I would recommend is, when you're talking about iteration, if we make that ridiculously tiny, clear all that. Two seconds. Where is it? There we go. Right. So if I go 0, 0, again. Right, what you see now is we've got an initial response. But now what we're recording is mass amounts of data sets. So we've got 1,000 particular point outputs. So me just by changing the value allows me to, to make them iterations even smaller. However, one thing that you should keep in mind is if you go a little bit bonkers with it. So if I go, where is that? Oh, let me just close that. Where's it gone? That's it. So if I go really bonkers with it and make it super small, you'll notice now, see on the simulation, it's now as down as pause. Now it's just running, and it's still running, and it's still running, and it's still running, and this is purely because the amount of data that I'm recording is way over the top. what I can end up doing, let me just pause that. I just want to see how far it's got. So that's just me running it for that amount of time. I'm already on, what's that? 660. No, it's at 6,625,500 and 5,481 lines already. So my point is you must be smart in how you're setting up these iterations. I'm just going to see if that will let me plot it, just because I'm interested about how this will be looking. I'm guessing that a plot like this will start to, well, yeah, you look now, it's actually only just got to that particular rise point. So, and I'm only at to the power of 7. So it's, yeah, what you've got to do is you've got to look to see how accurate these things are becoming. Now, the most common way of being able to do that is using the exact method. So if I come back, come onto here, onto the first order, and then we come back again. Now what I meant is with this particular equation here, what I would recommend is that you have a go at modelling it. The initial process that I've set up there is dead straightforward to do it. I would say have a go at modelling it and have a go at plotting that over the top of it, because all I've done here, gotta get myself mixed up here. All I've done here is I've plotted the two together. There's no reason why I can't plot over the top. Now I'll just show you how to do that, so you can have a go with that. So if I go T, vel, this will now plot the two together. I know that these labels are wrong, so yeah, don't jump on me too quick for that one. The trouble is, I suppose that my data set's going to be completely different here. Let me have a look where we're on. Yeah, vectors need to be the same length. It's really because my data outputs, the vectors that have been produced on both velocity and my dy and my position are actually slightly different. So they need to be the same length, but on my positional states, on this equation here, they are actually plotted as the same length. What I'll perhaps do is I will probably write that solution myself and then put this onto the team site. Again, I'm sure there's a few of you who will be very confident in doing that. I do want you to just get into that flow of being comfortable of being able to do that and getting comfortable in into script something like that. Being able to do something like that, especially for something like mechanical reliability, which for those of you who are meeting Ted in the next 20 minutes, Ted's incredibly proactive in this type of stuff, and knowing this type of thing for scripting in such a way is really useful. So I would always recommend just learning these skills. Again, this was just a bit of a warm-up to Matlab. What we will be doing is moving aggressively along into multibody. We'll be moving into Simulink. We'll be moving really quickly into Simulink. If anybody really wants to just get themselves warmed up to Simulink, which I totally get, you're welcome to just click on Simulink, and this will show you Simscape, it will show you examples, it will show you templates. On your examples, you've got some great examples to have a look at. So you see that one of the most common ones is the aeroplane landing gear. We will be doing things along this line. Having this little bit of a background knowledge is useful, because when I throw you into your assignment, I'm actually going to ask you to model air resistance to ensure the accuracy of whatever it is that you're modeling. It isn't just simply sticking things in there to get a result. I will be looking for the depths of things, because I do try to test you as much as I can in this. When it comes to the SolidWorks side of things, again, I'll be running this type of stuff, but also in SolidWorks. Now, the thing is with SolidWorks, when it comes to something like this, SolidWorks will struggle. incredibly struggle to be able to solve something like this, and it's just because there's no real volumetric elements to it. These are key dynamic components of a system. So I'm going to look at a different option for how to present that tomorrow. Again, we will be doing this as of next week, and what we will be doing is going into modelling of wheels, looking at wheels, looking at the torque on wheels, looking at the mass, the displacement, and looking at prediction of how things are behaving. I've actually just had a comment about the assignment. That is a that is a very ambitious assignment, and I must admit, great idea, like it. As we're going through, keep that in mind. I do really like that idea as an assignment. Keep that in mind. There's a lot going on in that. I did have one student last year who was interested in looking at, I don't know who saw this, the tug of war between Tesla's Roadster and the Ford. When that thing's pulling apart, that Tesla just ripped through that Ford like you wouldn't believe, and it was amazing to watch. But I was interested in the motor. What type of motor was used? What type of power was being put out by that Tesla to be able to do what it did? So I had a student last year who was looking at recreating that. But yes, so as I said, next week I'll be giving you geometries. We're going to start using this aggressively, and I just thought this was a bit of a nice warm-up, just because I didn't want you all to come in here and go, oh my god, nothing's installed, what am I going to do? We're all going to fail, it's all downhill. So don't worry about that. I just wanted to get you all into that way of thinking. I'll be freeing up more notes on Blackboard just to get you all working at it as well. The other thing I've not told you is I must have around, apologies if you can hear my dogs, I must have around 15 to 20 hours extra that I've got on YouTube that I'll be freeing up as well, just using this system. So again, I hope this was just a nice, steady introduction to the use of Matlab. For those of you who are mechanically based and did sit Matt's first year module, what I'm hoping to do is really complement a lot that you've done there. For those of you who didn't do it, don't worry, it's nothing that's going to hinder you at all. It just, for those who had to sit there all that time, it will make an awful lot of sense. Right, so what I'm going to do is I'm going to pause the video that I've been doing, so I'm just going to stop that.